So we're going to use the position function, number 2. In this f of t is given position, t cubed minus 9t squared plus 15t plus 10. And the first thing it asks for is to find the velocity at some time t. And based on our discussions, we had this discussion last week, that the position function, when you take the derivative of position, feet per second is velocity. And when you take the derivative of velocity eventually, or the double derivative of the position, we're going to end up with acceleration. We talked about that last week. We're going to do a lot of examples, but I'm going to say this again, kind of like the P to Q situation. I'm going to say it about 9,000 times, all right? So we know that when we have position and we take the derivative, we're going to end up with velocity. So letter A is just find f prime of t, which I'm going to label as v of t. So I take the derivative of t cubed, which is 3t squared. The derivative of negative 9t squared is negative 18t. And the derivative of 15t is just 15. The derivative of 10 is 0, like pi squared, like 189.4. Any constant is 0. Then it says in letter B, what is the velocity after 3 seconds? Oh, okay, so letter B is asking for v of 3. Right? That's what this is. This is v of 3, this is v of t. Alright, so, got to grind it out. Got to stick 3 in. Not make any math mistakes. Which should be proven. And I notice immediately that v of 3 is going to be negative, and the units were feet per second. And again, I know this is a big deal. Units are huge on these problems. All right? So I just answered letter B. You know, just plug and chug. I hate to say it that way, but that's what letter B really is. So I make them a little smaller, get them up high so I can kind of go back to the top here. So there's A and B. Now, this is where I started to butcher it last week. When is the particle at rest is the next question. The particle is at rest when the velocity is 0. So for letter C, I want to find times t's where v of t equals 0. Now, everybody, when we look at A, we have v of t. It's a quadratic formula. But I rarely do this, and I always want to factor first before I start doing negative b plus or minus b squared minus 4ac over 2a, and you don't even, that's completing the square. Before you complete the square or do the quadratic, we want to factor letter A. And I can factor v of t. I pull the 3 out, I get t squared minus 6t plus 5. And because I didn't butcher the problem incorrectly, you'll notice it factors into t minus 5 and t minus 1. And if 0 equals that, a times b equals 0. We know either a is 0 or b is 0. Well, in this case, the two times are 1 and 5. So the particle is at rest at 1 second and 5 seconds. All right? And this is going to be important for us because this is a intermediate value theorem type of thought process. Guys, if it's 0 at 1 and 5, we know, and it's negative here at time 3. We're going to know some facts here because we're going to be able to position this because we know when the particle's moving, it just doesn't go from negative 12 feet per second to 10 feet per second positive. If it's going to make the jump, it has to go through everything, including 0. This is a continuous function when we looked at it. Do you guys agree? Because it was a polynomial. The derivative is a polynomial. It is continuous. So we're going to use those schools of thought in the future. But today, it just asks, when's the thing at 0? Well, it's at 0 at 1 and 5. So there's A, B, and C. All right? If I move those up, can I fit them? Oh, look at that. How pretty. All right. So there's A, B, and C. Letter D. When is the particle moving in a positive direction? When is it positive? Is when it's when the velocity, when it's moving in a positive direction. Guys, you can be at a negative position and be moving in a positive direction. That's the hardest part usually for us to get. But it's just asking, when's the velocity greater than 0? And the reason it asks you in letter C to find the particle at rest is those will become our key points in our sign table. So if we start talking about the velocity here, and again, I'll write the velocity function below it, and I'm going to keep it factored. I much prefer to use the factored one. I'm going to make a sign table this time, and you might not need this level of detail to do this, okay? But I'm going to make it complete. The 3 is always positive. I don't need to worry about that. But the 2 binomials affect my sign. And the times I'm going to put in here are 0, 1, and 5. And I know at 1 and 5, the velocity is 0. I figured that out in letter C, right? I already know those. And I'm going to plug 0 into my equation up here and find out that at 0, I have a positive velocity. And I just plug 0 right here, guys. I take negative 5 times negative 1 is positive 5. And if you want, you can write it down, the value. I suppose it's 15 feet per second. I truthfully don't care about the value, and because it didn't ask for the velocity. I just like to check the 0. I want to know right from the get-go, where's it going? So everybody, between 0 and 1 in this interval, say it's half. Both of these are negative, so the particle is moving forward. In this interval, between 1 and 5, maybe I use time equals 3. It's negative, positive. Guess what? Between 1 second and 5 seconds, that particle is traveling with a negative velocity. And guys, we knew that. We knew that from letter B. It was negative 12. All right? And then after 5 seconds, it's positive, it's positive, it's positive. So the question asked, when is the particle traveling forward? It's traveling forward in 2 spots. And knowing that the domain starts at time 0, I would say the time has an element where v of t is positive of 0 to 1, not including 1, and from 5 to infinity, not including 5. Because at 1 and 5, the velocity is 0. That is not positive, that is not negative, it's just 0. It's our special point. So, that is the answer to letter D. It is moving in a positive direction, or I'm going to say it has a positive velocity between those intervals. And again, all that work for that little answer. All right? Letter E, find the total distance traveled during the first 8 seconds. And this is kind of what I want to make sure we get. So for letter E, I want to think about it this way. I have 8 seconds to graph, and this particle is moving along a line. And the first thing I do is I want to know what's happening at time equals 0. And this is a position problem, guys. So I'm going to do f of 0, not f prime, not v. I want the position. So I'm going to go all the way back to the original function. And I love the intercept because it's easy. 0 minus 0 plus 0 plus 10. This particle is starting at a position of 10. All right? At time 0, it's 10. And I know from the previous problem, again, you see why they do these big letter problems. You should understand that initially, out of the gate, which direction is this particle going? You should know from letter D that this particle is going forward. We figured out, in fact, we gave a value, but we didn't care about a value. We just know that it was, that's the wrong button. We knew that it was moving forward. So right now, until time equals 1, it is moving forward. And we know that at time 1, it's 0, then it goes backwards from 1 to 5, and at time 5, it's 0, and then it's going forward. So our next interesting point is where the derivative is 0, where v of t is 0. So our next interesting point, I'll do it in green, is time 1. And again, I'm interested in the position, so I'm going to do f of 1. Where is it at 1? Well, I put in 1 up here again. All right? And I get 1 minus 9 plus 15 plus 10. Negative 8 plus 25. I get that this is 17. I suppose I can put units on these guys. This is feet, this is seconds. This is feet, this is seconds. And when I talk about the particle, right now, it's doing one of these. It has gone to 0, and it is starting to go the other way. All right? It is starting to move the other way. It is turning around that letter E. So now, what's the next interesting time I'm interested in? Well, it's going to travel backwards until when? Till 5. So I'm going to put time 5, and I'm not sure if I'm going to be right here. I assume that the position of time 5 is going to be way back here. I'm guessing. So I'm guessing this particle is going to come all the way back, travel way back, and then do another curve here. That's my guess. And the only way for me to find out is to plug 5 seconds into the original function right here. And now I'm going to need a calculator. Even I don't want to do this. I don't want to make a math mistake because it's 5 cubed, so it's 125. I'm going to grab my calculator. 5 to the 3rd power minus 9 times 5 squared plus 15 times 5 plus 10. Plug in my old calculator. Oh yeah, negative 15 feet. Everybody, what's happened in this particle this time? At time 0, it started at 10. It went to 17 feet at time 1, turned around, traveled all the way to negative 15 feet at time 5, and then turned around again, and it's going to go positive for the rest of the time. But we're going to only go to time equals what? We're going to go to time equals 8 seconds. And again, I'm going to guess that it's going to be over here. And I want to know this. So again, I'm interested in the position at time 8. So I want f of 8. And again, got to use our position function because I'm interested in the position. Because I want to know the distance here. And to know that, I got to know the whole distances. So again, I'm going to use my calculator. 8 cubed minus 9 times 8 squared, which is 64, plus 15 times 8, plus 10. Boom! 66 feet. All right. And I just did letter F. Draw a diagram like figure 2 to illustrate the motion of the particle. I just diagrammed the motion of the particle. I needed F to do E in my opinion because now I got to do the total distance. So here I am. Everybody, I travel right here. Do you guys agree that 17 minus 10 is 7 feet? 17 to negative 15 is 32 feet. And then negative 15 to 66 is 81 feet. I just figured out each distance of each part. And now I got to sum them up. 88 plus 32, 90. When you add 81, 32, and 7, I'm pretty sure you get 120 feet. All right? So the total distance of this problem is 120 feet traveled. Let's be clear. That's the total distance. What if I ask for the total displacement change in the first 8 seconds? The total displacement, PSIP, total displacement, guys, is simply 66 feet minus 10 feet. This particle only moves 56 feet. It moved 56 feet by going from here to here. That's its displacement. But it did a lot more distance than that. It did 120 feet of moving around. All right? And again, this is the diagram. Letter E and letter F are together. So this is E and F and E. This comes back to the same idea when I talk about position are displacement and distance, or my position versus my distance. If I go for a jog in the morning, I usually jog about 2 or 3 miles. I don't tell you I have a displacement of 0. I stepped out my front door, ran a circle back to my front door. The displacement would be 0. I tell you my distance, which is 2 miles. Likewise, this particle, if you talk about distance, it moved 120 feet in the first 8 seconds, but it only displaced 56 feet. Big difference. We have to understand that difference. We have to make decisions about what's happening, okay? This is the first step in understanding this. It gets much more complicated because eventually I'll ask questions about speed. Is the velocity increasing or decreasing? We'll have to start to think about it like a car, because you can have a negative velocity that's increasing. Think about reverse in your car. When you put it in reverse and tromp on it, you have a negative velocity and you're accelerating. So that means you're going faster and faster backwards. But as soon as you let off the accelerator and start to brake, you're still going in reverse, but you're slowing down. Your acceleration is actually the other way, trying to go positive. It becomes very much something we have to keep track of. Great pictures, great diagrams, lots of space, all right? All right, that is a displacement problem.